Assalamualaikum warahmatullahi wabarakatuh. My name is Arif Hami. So I'm going to brief to you all about the introduction and the basic principle of the refrigeration system of this journal. So refrigeration system is a process of reducing and maintaining the temperature of specific surrounding. So it can be accomplished by removing heat from the body that being refrigerated and transfer it to the another body or the surroundings. So there are few application in the industry of the refrigeration system, which is the first one is the food and beverage industry, the second one is the pharmaceutical industry, and last one is district cooling industry. So we're gonna move about the introduction of this journal. So since 1990, vapor compression refrigeration system is operating with the usage of the R134A refrigerant. So but the refrigeration system that use R134A have a high energy consumption and it produce a significant environmental impact. So the purpose of this journal is to develop the new energy efficient vapor compression refrigeration system that can operate with the ecological refrigerant. So the author designed an energy efficient system that have low cost and operate with a most appropriate ecological refrigerant. So on this journal, they are focusing on the usage of the R290, R600A and R1234YF. So the basic principle of this journal is two. The first one is environmental analysis, which is based on the total equivalent warming impact, and the second one is thermoeconomic analysis, which is focusing on the coefficient of performance, energy efficiency, and the total plant cost rate.
For my part, I'm going to talk about schematic drawing and explanation. For first diagram is about how the cycle of refrigeration works. As you can see, the refrigerant leave from evaporator and enter the compressor, then condenser, then thermal expansion valve, then through the evaporator, then the cycle will be rotated. So in essence, it is using the vapor compression refrigeration cycle to cool water for air conditioning while also recovering the rejected heat to produce hot water for bathing. So basically the cycle taking advantage of both cooling and heating needs. Okay, for second diagram is called subcritical refrigeration cycle for R2900, R600A, R134A and R1234YF. As you can see from the slide, it already explained what will happen when the refrigerant enter from one state to another state. The area under each curve represent the cooling effect produced by the evaporator. So basically it represents the subcritical vapor compression cycle on pressure versus enthalpy diagrams for each refrigerant to make it easier for evaluating their thermodynamics characteristic.
Okay, as from my part, it's about performance calculation of the system. So here's some of advantage if we perform calculation of the refrigeration system. So this is an example about how we're gonna find exergy disruption for expansion valve. So since expansion valve is in state between state 3 and state 4, so for exergy disruption, we need to use formula exergy flow state 3 minus exergy flow state 4. So the P0 is given and the T0 is also given. And also mass flow rate for refrigerant is 11.7396 kg per second. For the first step, we need to find H0 and S0 on the state 0 since T set is less than T0. So state 0 is superheated vapor region. But you have to do interpolation because the value is between, so we have to do interpolation to get the accurate H0 and S0. And then for state 3, do the same as the state 0 also, but for state 4, H3 is same with H4 since they have the same pressure. But for state 4, you need to find S4 using the formula as I write in the slide because they are saturated vapor liquid mixture, so it's on the center of the graph, so you need to use the formula. And when you get the data, you have to insert in the equation, so you will get the value of exergy flow for state 3 and the value of exergy flow for state 4. And then you minus it and you get 21.69 watt, which is the same as the journal that we picked, which is the exergy disruption for refrigerant is 21.69 watt.
My name is Chikawai and I'll be presenting on method of performance analysis. So there will be two methods that will be used to compare refrigerant 290-600A, 1234YF and 134A. The first method is environmental analysis, which uses total equivalent warming impact. The second method is thermoeconomic analysis, which uses COP, exergy efficiency and total plant cost rate. For the environmental and economic analysis, the direct total equivalent warming impact and indirect total equivalent warming impact is added up to count the total equivalent warming impact. For the total plant cost rate, the total of capital and maintenance cost rate, operational cost rate, and penalty cost rate due to CO2 emission is calculated. For the energy and exergy analysis, COP is calculated using cooling capacity, which is divided by the total of work of compressor, adding the work of evaporator, adding the work of condenser. The exergy efficiency is calculated by using 1 minus exergy destruction over work of compressor. Based on these methods, the best refrigerant is R290 as it has the highest environmental energy, exergy, and economic performance. It should be noted that R290 and R600A has higher COP by 44.3 and 6.6% than R134A, and it has higher exergy efficiency by 44.6 and 6.5% than R134A. Exergy destruction for R600A is 85.6%, 1234YF 193%, and 134A 108.1%. It is interesting to see that most of the exergy destruction occurs in the compressor. The baseline sets for temperature of evaporation is -3 degrees Celsius, while the temperature of condensation is 45 degrees Celsius. Thank you.
Hi everyone, I'm Danish Hakim and I will continue present on improving the vapor compression refrigeration system based on a detailed thermoeconomic and environmental analysis. Our goal is to identify the best refrigerant and system configuration to enhance the vapor compression refrigeration system. We will focus on environmental impact, energy efficiency, exergy efficiency, and economic viability. The vapor compression refrigeration system currently uses R134A, which has high environmental impact, suboptimal energy and exergy efficiency, and higher operational costs. We aim to find better alternatives. We evaluated different evaporation and condensation temperature and copper tubes diameters for both the refrigerant and water sites, considering total equivalent warming impact, coefficient of performance, and exergy efficiency and total plant cost rate. The optimal conditions. We found the best performance at an evaporation temperature of -3 degrees Celsius and a condensation temperature of 45 degrees Celsius, improving all metrics. The environmental performance. The R290 refrigerant showed the highest environmental performance with a total equivalent warming impact 144.5% lower than R134A. We suggest replacing R134A with R290. The energy and exergy efficiency. R290 also excelled in energy and exergy efficiency with a coefficient of performance 44.3% higher and exergy efficiency 44.6% higher than R134A. R600A is also a viable alternative. The economic performance. R290 had the lowest total plant cost rate, mainly due to its lower electrical power consumption, reducing operational costs. The exergy disruption analysis. R290 showed the least exergy disruption, especially in the compressor. We recommend optimizing compressor efficiency and regular maintenance. In conclusion, implementing these improvements will enhance the vapor compression refrigeration system's environmental, energy, exergy, and economic performance. Transitioning the R290 is crucial for sustainability. Thank you for your attention.